All right, guys, so now we're looking at Doppler effect, all right? Doppler effect, we're going to start with sound because sound is something that's easy to visualize, a little bit slower. And then we'll look at light, okay, by inferring that similar things happen, right? Which is what we do a lot in physics, is we trust that the physics stays the same, though we will mention a couple of changes that are going to affect things slightly. All right, so we're going to start with drawing some pictures because this will help us to really visualize what's going on and understand. So we're going to go ahead and start. I've got a dude here at number 15. Each centimeter here, just so we have a scale, 1 centimeter is going to equal 100 meters. All right, we're going to have a dude down here at 25. And we're going to have a dude down here at 5. So each one is about 1 kilometer apart. Okay, dude in the middle has a nice speaker set. Okay, so he's got his speaker here, and it is blaring out sound. All right, so the dude is going to be moving to the right at 100 meters per second. Okay, so he's going to move along 1 centimeter in our drawing. And then the sound, which I'll do the sound as red, just so it's easier to tell apart. The sound can obviously move in both directions at about 300 meters per second. I know it's a little more than that, 330 plus or minus a little bit, but in order to simplify our drawing here, we'll go ahead and do that. All right, so this is initially, right? That's where they are. Now, we'll go ahead and do the first 3 seconds here, okay? So after 1 second, dude is now on the 16, right? I'm sorry, he doesn't have any better name than that. The other guys are just hanging out where they are. So they're gonna stay here at 5 and at 15 indefinitely, at least for the 3 seconds that we care about here. Sorry, 5 and 25. Yeah, I know my drawing skills are amazing. Get over it. All right, so dude has moved to the right. Okay, now the sound that he created in the initial at time 0, right? Because this is time 0 here. Okay, the sound that he created at time 0 was here at 15. But in a second, each of those sound waves is going to move away 300 meters. And so the one that was right here is now, instead of at 15, is now going to be at 18 because it's moved to the right. So here is that sound wave. It's at 18 now. Okay, the one that was on the left-hand side has moved 300, 1, 2, 300 in the other direction. So it's now at 12. All right. So here we go. We got a drawing. So there's the sound waves. Now you'll notice that it isn't very well centered on him. That's because the waves move along at their constant speed of 300 from the center, from where they were created, right? He has actually moved over to the right, and so therefore he's not in the middle of those 2 sound waves anymore. All right, let's move on to, so that is a picture of time 1. Okay, but now let's move on to a picture of time 2. What's going to happen? Well, dude who is at 16 is now going to be at 17, right? The sound that was at 18 is now going to move 3 more over to the right, and that's going to be at 21 now, all right? The sound that was at 12 is going to move 1, 2, 3 to the right, and that's going to be down here at 9 now, right? So that's that wave front, right? Okay, now I'm going to switch colors slightly because I'm going to show the wave that was emitted, the wave front that was emitted at this point in time, okay, at time 1. So that was at 16. It's now moved 3 to the right. So 1, 2, 3. So there should be a new one at 19. So this is the wave front that was created at time equals 1. Now, obviously, there could be wave fronts in between those times, but I'm just trying to give you a simple drawing so you can get a good idea of what's going on here, right? Then from 16, it'll go 1, 2, 3 to the left, which will put him right at 13. Okay, so that's the second one. We'll be right here at 13. All right, and that's time 2. All right, we're going to go 1 more second just so you can see clearly what's going on here. right? So dude is now going to move over to 18, which, sorry, my thing at the bottom makes it so you can't see the numbers, but it is lined up with all the others, right? All the 18s are lined up, all the 15s are lined up. So dude is over on 18 now. Okay, now that he's there, okay, let's look at the red one. The red one's going to move 3 to the right. 1, 2, 3. So the red one's going to be to the right at 24 now. The one over here on the left, which is at 9, is going to be 1, 2, 3. So that one's going to be at 6. That wavefront is moving to the right. Okay, now we've got this wavefront, the purple one, which is still moving at 300 meters a second. Okay, but it's at 19. Hi, that's my nephew Will. Will, say hi. Oops, sorry, I flipped the screen. All right, so we were at 19. We're going to go 3 to the right, so 20, 21, 22. So the purple one's at 22 now. And this one moving over to the left would be at 12, 11, 10, moving 3 to the right. So I'm going to put it right there at 10. Okay, which you can see is in the right place. Then we'll add in one more because we're going to add in the wavefront that was created at time equals 2. So that was created at 17, which means 3 to the right, 1, 2, 3 would put 1 at 20, and 3 to the right, 1, 2, 3 would put 1 at 14. And so in this picture, it was being created. That's the wavefront that was created at time equals 2. It's now had a second to move to the left, and then 1, 2. And so this one would be right here at 20. All right. Now, what I want you to see is this. Can you see the difference in the waves on the right and the waves on the left? All right. Well, here it is. The ones on the right, they're closer together, right? It doesn't mean that the actual sound being created is changing. What's changing is the way that this guy is going to perceive it. The sound being created is exactly the same as it used to be, right? The difference is that this guy is moving in that direction. So by the time the wave fronts approach this guy, because he's moving to the right, by the time the wave fronts approach this guy, he's going to hear a shorter wavelength, right? He's going to hear a shorter wavelength. Now, if the wavelength is shorter and the speed of the waves is the same, right? Because the waves are still traveling at 300 meters a second. What does that mean? V equals wavelength times frequency. If the speed of the waves is staying the same and the wavelength is decreasing, that means the frequency is increasing, which means he's going to hear a higher pitch. That's how the Doppler effect works. Okay? Now look at the guy on the other side. Look at this guy. Okay? Now again, the wave is still moving at exactly the same speed. It's still moving at 300 meters a second. But because this guy, the center guy, dude, is moving away from him, what happens to the wavelength? The wavelength, if these are my wave fronts, is now a longer wavelength. Similarly, V equals wavelength F. If the wavelength is increasing, the frequency and therefore the pitch is going to decrease. All right? So, there you go. That's Doppler effect in a nutshell. Because of something that's moving, all right, because of something that's moving, the wave has an observed value that is different from the value that's being sent out. All right? All right, so this is a snazzy little applet here. It's going to show us kind of what's happening in Doppler effect, right? So here's my source, this red guy right here. And then I've got the receiver, which is a microphone. All right, so right now we're not hearing anything because we're so far away that we just don't hear very much. Go ahead and move the microphone a little bit closer, okay? And what do you hear? It's not very loud, but you can hear it. It's constant, right? We'll go in a little bit closer. And you can hear that the frequency is the same as it was before. Looking at the wavelength close up from one crest to the next and looking at the wavelength far apart, it's basically the same, right? And so what changes when you go further and closer is just the intensity, how loud it is, all right? Now, of course, what I'm going to do is I'm going to get the source to move, all right? So as the source moves, let's see if we can speed it up a little bit here. There we go. So now you can see the wavelength on the right is shorter, the wavelength on the left is longer, and we're about to hear the frequency, right? You can hear it's faster than it used to be. Now, it's a little weird as the source goes through, but now it's on the other side, and you can hear as the source is going away that the frequency is less. Now, this corresponds to a lower pitch, right? The less is a lower pitch, and then the higher frequency is a higher pitch. And so that's why you get, you know, when the sirens go by or when you hear a race car go by, you hear the meow, because you hear the high pitch and you hear the low pitch. Now you kind of hear that little swooping, that meow, because it's not right in front of you. When we looked at it, we heard a high frequency, and then right afterwards, there was a low frequency. I'm going to try to do that this time. I'm going to go a little bit off to the side. Okay, and this is what it would be like for the car. Okay, so you hear it's high, and it's changing. You can hear the changing of that frequency. It's not an instantaneous thing, right? And so that's why you get the little swoop of the car or the siren or whatever as it's going by. Recognize, though, that the big thing with the Doppler effect is it's high, and it started high, and then as soon as it passes, it's low, okay? And it's constant, right? It continues to be constant. We can see that in the picture as well, all right? Just for the fun of it, I'll show you what happens if we put it at the speed of sound. So right now, we're going to have our object. So now the object is traveling at the speed of sound. So here it comes. It's going to come back. You can see this sound wave, this compression of sound waves. Remember, sound is just a compression or rarefaction of air. So I've got a whole bunch of compressions right there. So I get a whole bunch all at once. If I can get straight in front of it, right? It has one really big loud one at the beginning. That's the sound barrier. Like when airplanes are trying to break through the sound barrier, there's literally a barrier there, right? There's a barrier of air, which is the sound that's been all compressed together because of all of these interference, all these constructive interference of all those waves, all those particles. There's a physical barrier of air there that you have to break through, right? Now, once you get through, you'll see that it's easy to continue forward after that, and the sound is now behind you. And so a person who is down on the surface, like on the ground, is going to see the jet flying over, and later they're going to hear the sound. Oh, the sound didn't quite get to me. I was too low. But anyway, you get the idea. All right, we're going to go ahead and go back to the other slides now, and we'll talk about some equations, some math. That's it. All right, that was nice. How about some equations? All right, how about some equations? Now, these are the equations that we're going to use when dealing with the Doppler effect. All right, first we have a source that's moving, okay? Because there's two different scenarios. One is that the source is moving, and the other is that the observer is moving, all right? So, if the source is moving, right, what we have here, the F is, the original F is F right here, okay? So we've got F, which is the frequency at the source, okay, that's the original frequency right here. We've got V, which is the velocity of the wave, right, so that's on both the top and the bottom. We've got F prime, or F apostrophe, which is the apparent frequency. That's what's being heard by the observer because of the moving source. And then you've also got US, right, which is the velocity of the source, right? So that's the speed of the source. Now it's a plus or minus because we saw that when the source was moving, the guy on the right got a higher frequency, the guy on the left got a lower frequency. Now this is where you're going to have to think a little bit, right? Because this is the equation given to you in the packet. You have to make the connection that if my source is moving towards the observer, this is an ear, so it's going to hear. So if it's moving towards the observer, we know the frequency needs to be the observed frequency, apparent frequency, needs to be higher. Now, in order for that to happen, the denominator needs to be smaller, right? Because this isn't going to change, that's not going to change. So this needs to be smaller. So therefore, I'm going to want to subtract the source velocity, okay? If my source is moving away, then I know that I want my frequency to be lower. And so therefore, I want a bigger denominator, and I'm going to add the two velocities together. All right, so you have to make that choice, and you have to make that decision to make sure that everything is working out okay. So you have to have the conceptual understanding. All right, now there's a second equation. Personally, I like to just put them all in one equation, but IB has split it up like this for you so that now you have a different equation for a moving observer, okay? And you'll notice that now the velocity given to you, these are all the same. All the other variables are the same. Apparent frequency, this is the observed frequency. This is the frequency at the source. This is the velocity of the wave itself, which depends on the medium, not on the source or the observer. So now we've got this guy right here, which is a moving observer, right? And so again, you want to recognize if the observer, here's the observer, let's stick with our convention. So here's the observer, he's hearing. If he is moving towards the source, then we expect the frequency to be more often. We expect a higher frequency, because if he's moving towards it, he's going to hit those wave fronts more often. Okay, that means we're going to add the velocity of the observer, right? This is the observer. We're going to add the velocity of the observer because we want the numerator here to be larger, and a larger numerator will result in a higher frequency. And of course, the opposite is true. If my observer is moving away, then it's going to take longer for those waves to hit me, and if those waves take longer to hit me, then I'm going to hear a lower frequency, and a lower frequency, this is observed, lower frequency means that I want a lower denominator, and so I'm going to subtract. All right, so it's not so much right or left, it's is it moving towards the sound or is it moving away from the sound? All right, so these are the equations you're going to use. Let's go ahead and look at an example. Okay, here we go. We have a stationary loudspeaker emitting a sound frequency of 2 kilohertz. A student attaches the loudspeaker to a string and swings the loudspeaker in a horizontal circle at a speed of 15 meters per second. The speed of sound in air is 330 meters per second. An observer listens to the sound at a close but safe distance from the student. All right, so picture, we need a picture. Here is said student. The student has a string. On this string, they've got the speaker. This is the speaker which is creating sound. And then he's going to swing it in a circle going around him. So it's going to swing around like this. So it's going this way. It's going to go that way, right? So it goes around the circle like that. Okay? Now we've got our observer, which is going to be over here. It's just round because it's just his head. You can see him from the top. And luckily they have tattoos on their head so that we know which one's the student, which one's the observer. So we got the observer over there. And hold on. We got the observer. So the questions are, explain why the sound heard by the observer changes regularly. All right, this part is fairly straightforward. The answer being that because sometimes, you can see in my drawing, sometimes the velocity of the speaker is, or the source, the source is moving towards the observer, which means it's going to hear a higher frequency. And sometimes, because I'm going in circles, sometimes the speaker is going to be moving away. And sometimes it's actually moving parallel, which means I'm actually going to hear the frequency I'm supposed to. All right? Now, yeah, and so sometimes I'm going to hear a lower frequency. One thing to recognize is that distance has nothing to do with it. All right? Obviously, if you're far away, the intensity will be less. But being closer and further has nothing to do with the frequency. Frequency is 100% due to the motion, moving towards or away from an object. Okay? Sometimes students have the feeling that, oh, because it's closer, it's going to be a higher pitch. No, that's not true. In fact, the pitch here and the pitch there is exactly the same. They'll hear exactly the same note, right? They'll hear exactly the same frequency. What will be different is it'll be louder here and it'll be quieter there, okay? Maybe or maybe not significantly, but that's all that happens because of distance. What matters is, are we moving towards the observer or are we moving away from the observer? All right? So now we've explained why the sound changes regularly, because we have a changing velocity towards and away. Now, determine the maximum frequency of the sound heard by the observer. All right? So, you'll need to find another sticker. Go find one. Go find one. So, what we're going to do is we're going to use the equations that we just learned. We've got a moving source. So for the moving source, it is f prime equals f times v over v, either plus or minus us. Okay? We want the maximum frequency. So maximum frequency, that's the higher pitch, is going to be when the object is moving towards the observer. So that would be this point right here. All right? Now, the observed frequency is what we're looking for. We do have a original frequency was given to us. The original frequency was 2,000 hertz. Okay, 2 kilohertz. I'm going to put it in hertz because it should be in our SI base units. All right, we've got the velocity of the sound. It's a sound wave, so we're going to put 330. Okay, and then on the bottom we'll have 330. Now we need to put the velocity of the source in there. Now the velocity of the source, of course, I need a plus or minus. We already talked about the fact that we're looking for the maximum, so we want the frequency to be as high as possible. So in order to do that, I need the denominator to be as small as possible. So in order for that to work, I'm going to go minus the speed of the speaker, which is 15. And so now I should be able to type that straight into my calculator, and I'll go 2,000 times 330 divided by 330 minus 15, and we get our final answer of 2,095. Now I do see that I got 3 sig figs here. Those are only 2. So you could write that either way, but I'm going to go with 2,100 hertz because I'm giving it 2 sig figs. But the number I got on my calculator was 2095.2381. All right, so not too bad, right? Should be fairly straightforward and fairly simple as long as you're using the correct formulas and putting things in the right way. All right? Okay, lovely. Let's move on to another one. Wait, but isn't light a wave? So shouldn't light have a Doppler effect as well? This is actually really interesting because there's a lot of things that we can do with Doppler effect of light and of sound. And we'll look at a couple of those in just a minute. Okay? Now, the problem with light is it's a little more complex because we were able to just kind of add and subtract the velocities, put things together. It's very straightforward when you're dealing with things that are slow. When we get to light, light always travels at the speed of light. An observer will always see something travel at the speed of light. Doesn't matter whether you are moving at the speed of light or whether you are going slowly. Every single thing in the universe will always measure light as traveling at the speed of light. And so it kind of messes things up because sometimes, if you're in a car and you're driving at 10 miles an hour and then you throw a ball at 10 miles an hour, an observer on the side of the street will see the ball traveling at 20 miles an hour. Right? Because it has the speed of the car plus the speed of the guy throwing it. Those get added together. It doesn't work that way with light. It's kind of weird weird, but it actually ends up working with all of the physics that we understand to this point. All right, so we're actually going to use a slightly different equation for light. This is the formula that we have to use for light. The change in frequency over the original frequency is equal to the change in the wavelength over the original wavelength, which is approximately equal to the observed speed over the speed of light. All right, so this is the formula that we're going to use, and you'll see this later as we go through an example. For example, right now, as the sun rotates, light waves received on Earth from opposite ends of a diameter show equal but opposite Doppler shifts. The speed of the edge of the sun relative to the Earth is 1.9 kilometers per second. What wavelength shift should be expected in the helium line having wavelength 587.5618? Okay, so again, like normal, we're gonna draw a picture. We've got the sun here, which is nice and yellow, but the sun is rotating, right? Just for sake of this picture, we're gonna draw it rotating this way. It doesn't really matter. You could look at it from the other side and it would be rotating the other direction. So this piece of the sun is moving towards our Earth, which is going to be the blue planet. So here's Earth. So at one point it's moving towards the Earth. At another point it's rotating away from the Earth. All right. So these are both Doppler shifts. All right. But we can't use the sound equation. What we're going to use is the equations that I just showed you. All right. So what we're going to do is we're going to take our formula, which is this: delta F over F equals delta wavelength over wavelength equals V over C. And so we are looking for the wavelength shift. So the wavelength shift is change in lambda. So we're not going to worry about the frequencies here. Okay, so we're going to go the change in wavelength. That's what we're looking for. Divided by the original wavelength, which was 587.5618 nanometers. Now, because this is a fraction, as long as I keep the units in each fraction the same, I don't need to worry about changing to meters. You could, but these two are both going to be nanometers and the units are going to cancel out, right? Over here, we're going to go equals the velocity. The velocity of those particles rotating on the edge of the sun is 1.90 kilometers per second. Now, I know that C is in meters per second, so I am going to write this velocity as 1900 meters per second. So that's the velocity of the source, right? And then I've got C, which is the speed of light, which is 3 times 10 to the 8th meters per second, just like that. Now that I've done that, I can go ahead and solve for the wavelength, which is just going to be 1900 divided by 3 times 10 to the 8th. And then multiplied by the 587.5618. And we get a change in wavelength of 0.0037. Let's see, I've got 4 decimal places there, so I'm going to go out to 4 decimal places here, 37. And so that will be the change in wavelength. Now, it doesn't seem like very much, but with sensitive instruments, we can actually measure that. And we can see the light on this side of the sun being a slightly different wavelength than the one on the other side of the sun. Okay? And obviously, you can use that to then find the frequency if you need to. All right? So, hopefully that makes sense, and you're getting an idea of how Doppler effect works. And let's... why do we care? Why do we care? There's actually quite a few reasons why we care. So here's one of them. Okay, astronomy. Let me give you an example. In astronomy, we're trying to figure things out about things that are light years away, right? Millions and billions and trillions of miles away. And, even light may take years or thousands of years or millions of years to get here. So how do we know anything about those? Well, here's an example. This is an absorption spectrum, right? This is what we see when we look at something. I believe this is for hydrogen. This is what we see when light shines through hydrogen. Now, our sun, we know, has hydrogen and helium, mostly hydrogen that is fusing to create helium. Now, on the outside of the sun, there's an envelope of gas. And so when the light from the sun shines through the hydrogen and helium that are on the outside of the sun, some specific wavelengths of light, you can see, get absorbed by that hydrogen-helium atmosphere, you could call it, or an envelope of gas that's on the outside of the sun. Okay, so this is what it should look like. This is what it looks like when it's at a basically constant speed, like the sun is, if we looked at the center of the sun, where we're not getting any rotational effects or anything coming closer or farther, that's about what we get. Okay, sometimes when we look at stars, we see these things, right? You can see in this second one right here that every single line, it's the exact same lines. This is why we believe that other stars are also made up of hydrogen and helium, because we see the exact same absorption lines. And those absorption lines only come from the specific makeup of hydrogen and helium. We see the same lines, but can you see that they've all been shifted over to the right? So they've all been shifted over to have longer wavelengths. Why would they appear to have longer wavelengths than what they should? Well, it's because the star is moving away. We call that redshifted. And so from this information, we can find out that some stars are moving away from us. Similarly, if you look in the one below, you can see that all of those wavelengths have been moved over to the left, right? From where it should have been, right? Again, really interesting that we can see those wavelengths move to the left. Why would they move to the left? Why would they have shorter wavelengths? Well, remember that picture of the dude moving with the sound waves? Well, it's because those stars are moving towards us. And so therefore there's blue shifting going on, right? All of those wavelengths, which should be at these specific places, right? That should be in these locations are all slightly to the left, meaning that they've been blue shifted, which means that that star must be moving towards us for some reason. This is one of the ways that we can learn about things that are far away, all right? It also works for radar. You've got all sorts of types of radar that we use nowadays. You've got radar for aircraft, weather radar. They use it in geology or archaeology. A speed gun, the police use a speed gun. That's all done by this. You use a gun, you shoot a wave to a source, the policeman points it at you, it bounces off of your car and comes back, and based off of the shift in the frequency of the wave that's been shot out, they then know how fast you're traveling, right? Obviously, if you're moving towards them, they should be getting a higher frequency, and based off of how high, they know how fast you're going, right? Sports as well. When you're looking at speeds of hockey pucks or baseballs or anything like that, it's all done with a radar like this, where it has some type of wave that's being sent out and bouncing back. Okay, this is neat stuff. What else? What else? Blood? Blood? What does blood have to do with this? Well, let me show you. Okay, unfortunately, I can't get rid of my... Oh, I can. So in the blood, you have blood cells that are moving, right? A lot of your blood is just plasma, right? It's just this liquidy substance. But there are more solid blood cells in there, right? And so what you can do is you can take an ultrasound beam, okay? You can stick it into the vein and shoot it down, and it's going to go down, it's going to go through the plasma, through the liquid, and it bounces off of those blood cells and comes back. Now, it doesn't matter how close or far, right? Close or far does not matter. What matters is what direction are those blood cells moving. And if we measure enough of them, we can figure out, of course, the angle is going to matter, all these, but if you measure enough of those, you are able to figure out how fast the blood is moving through a vein that is inside your body. So lots of really, really cool stuff that we can do with this, all right? So let's look at just a couple more examples just so that we can make sure that we're comfortable with these. And then we will move on to, we'll wrap up this video. All right. So we've got hydrogen atoms in a distant galaxy that are emitting light of wavelength 658 nanometers. The light received on Earth is measured to have a wavelength of 689 nanometers. So we've got a longer wavelength there. Right now, you should be able to state whether the galaxy is approaching the Earth or moving away. What is it? Good. So it's got a longer wavelength. Therefore, thinking back to our picture, even though our picture was sound, the principles are still the same. So that means that the object must be moving away. Okay, so we know it's moving away. Step one done. Now we want to calculate the speed of the galaxy. Now we are talking about light here. So because we're talking about light, we're going to use the delta F over F equals delta lambda over lambda. And we're going to use V over C. And of course, this isn't actually equal. Sorry, it's very, very close. There's a lot of relativity stuff that goes into that. But for our purposes right now, it'll be close enough. All right. So let's go ahead and put in our numbers. We're not really worried about the frequency here, so we'll go ahead and take that out. Let's put in our numbers for the wavelength. The change in wavelength, remember this is the change in wavelength, so I'm going to need to go 689 minus 658, which will give me 31. So the top will be 31. The bottom will be that's the real wavelength, right? So that's what hydrogen atoms should be emitting. So it's the 658. Be sure not to put in the 689. It's tempting to put that because that's what we're seeing, but what you want is the original. What was it before any motion was added in? All right. Now this we're going to say is approximately equal to the velocity all over the speed of light, which is 3 times 10 to the 8th, and we punch that into our calculator, beep, 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 and we get that the velocity is approximately 1.4 times 10 to the 7th meters per second. And is that fast? Yes, that's fast. That is quite fast. That's getting pretty close to the speed of light. I mean, not super close. I mean, we're still off by 1.5 orders of magnitude, but it's pretty fast that galaxy is moving away from us. And this is the reality, is that galaxies that are very far away are moving away from us very quickly. And if we do astrophysics, we'll talk more about that next year. All right. Let's move on. Let's go one more example because we can. All right, so we've got a sound wave of frequency 300 hertz, which is being emitted towards an approaching car. The wave is reflected from the car, received back at the emitter with a frequency of 315 hertz. So the question is, what is the velocity of the car? Okay, so I'm going to draw a picture because pictures are usually helpful. So the original situation is not this. We've got, that'll work. We've got a car which is moving towards dude who is sending out a signal. All right, so the signal originally is 300 hertz. It's going to the car, being received, and then being sent back. So here's what we have to do. We actually have to split this up into 2 pieces. All right, the first piece is the car, which is receiving the sound, and then it will send it back to the observer. All right, back to the original guy. So in the first scenario, we have a moving observer, right? The car is moving, the car is observing this sound which is coming towards them. All right, so we're going to use the equation for the observer. F prime equals F times V plus or minus UO all over the velocity of the sound. So I can put most of these numbers in already, right? I know I'm looking for this right here. F prime is the frequency being observed by the car, right? The car is the observer right now. Okay, so I don't know that, but I do know the original frequency was 300. I know the speed of the sound is given to me as 340. And I know that the car should be hearing a higher frequency, right? Because it's moving towards the source. And so I'm going to add on UO here, and it's all going to be divided by V. All right. Now, of course, which is 340. Now, the problem being is that we don't have either of those, so I can't actually solve it yet, okay? What I can do is now we're gonna look at the second scenario, right? So the second scenario is now that the car is the source, and it's bouncing the sound back to the man who is here listening, all right? And when it gets to him, we know that it's supposed to be 315 hertz. All right, so what is the frequency coming from the car? Well, it's F prime. It's that same F prime there, right? But now the observer is stationary and the source is moving. And so this time we're going to use the other formula, which is F prime equals F times V over V plus or minus the velocity of the source, okay? Now, be careful, because F prime here, this F prime is now the frequency that is being created. That's now the source, right? And so that is going to go here, okay? The frequency at the observer is 315, okay? And then the velocity, of course, we know is the velocity of sound. So what I'm going to do is I know that this frequency is the same as the frequency that was observed there. So this formula right here is actually going to go in for the frequency there. So this is going to go in, and so we're going to go 300 times 340 plus the original speed of the observer, which was the car, right, divided by 340. And then that is going to be multiplied by the 340 over 340. That's the 340. And I'm going to subtract the speed of the source, which is the speed of the car. Now I'm subtracting because it's moving towards, and I want a lower denominator so that I have a higher frequency, right? So all of this now, these UOs, these U's are the same, right? They're both the speed of the car, okay? So now I'm just going to plug this into my calculator, and when I plug it into my calculator, I'm just going to insolve. I'm going to go insolve all of this. Remember to put your comma X at the end, and it should give you the correct answer, which is that the car is traveling at 8.29 meters per second. And that's how you solve. This is a difficult Doppler effect question. All right, so now you've seen one that was easy, you've seen a couple of ones with light, and now you've seen one that's a little bit harder. And that is it for Doppler effect. So let me know if you have any questions, and we can move on and do